The other thing I want to go over again is effective nuclear charge and shielding. And I want to demonstrate that. For instance, if we want to talk about, say, uh, fluorine and then neon and sodium, 1s2, 2s2, 2p5, 1s2, 2s2, 2p6, and 1s2, 2s2, 2p6, 3s1 are their electron configurations. Well, if we were to draw a Bohr model of this, fluorine has 9 protons in the nucleus, so it's got 9 positive charges. Neon has 10 positive charges, and sodium has 11 positive charges. Then, if we were to try to construct a Bohr model, well, in the first energy level, fluorine has 2 electrons in the 1s. Then in the second energy level, we're going to put the 2s and the 2p together for this. It's got 7. 1, 2, 3, 4, 5, 6, and 7. The effective nuclear charge on these 2 electrons closest to the nucleus is a positive 9 because they feel the full charge of the nucleus pulling them in. The electrons in the second energy level have the electrons in the first energy level between them and the nucleus. So these two are our shielding electrons. So they kind of cancel out 2 of the charges from the nucleus. So the effective nuclear charge on the valence electrons out here is a plus 7. So I'll just make a note of that. So these experience a plus 7. These experience a plus 9. So all the valence electrons experience a plus 7. We don't differentiate between sublevels for effective nuclear charge because all the electrons in the second energy level have similar distances from the nucleus, and they definitely have the 1s electrons closer to the nucleus than they are. If we look at neon, it's going to have 2 electrons in the first energy level and 8 in the second. So some differences here. The effective nuclear charge on the core electrons, the ones closest to the nucleus, is going to be a plus 10. And the ones out here, the valence electrons, would be a plus 8. So that kind of goes back to that question about nitrogen and oxygen with the photoelectron spectra, is as you increase the charge in the nucleus, you're going to actually pull these electrons closer. For instance, if you go all the way down to, say, element 118, oganesson, the 1s electrons are experiencing a plus 118 effective nuclear charge. Right. If we look at sodium, it's got in its first energy level 2 electrons. In the second energy level, it's got 2 in the s and 6 in the p, so that's 8 electrons. And then in the third energy level, it has 1 lonely electron. So if we look at the effective nuclear charge, it's plus 11, plus 9, and plus 1. So the reason that sodium only forms ions that are sodium with a positive 1 charge is because it can easily lose this electron that's only being held by a positive 1 nuclear charge, and it's quite far from the nucleus. It's not going to lose more than 1 electron because these electrons are experiencing a positive 9 effective nuclear charge, which is pretty strong, and they are quite close to the nucleus. In fact, these electrons here would be pulled closer to the nucleus than the electrons in neon or fluorine because they're experiencing a greater effective nuclear charge. Similarly, neon, it's not going to lose electrons because of this plus 8 nuclear charge. Neon will also not gain any electrons because For it to gain an electron, it would have to create a new energy level out here. And if it were somehow able to gain an electron, let's just draw this in hypothetically. If neon gained an electron to have a -1 charge, this hypothetical electron out here would be experiencing 0 effective nuclear charge. So it's just not going to happen. Then if we look at fluorine, fluorine can gain 1 electron and become the F minus electron, or the F minus ion that was referenced on Friday, by sticking an electron right there. It's got an empty spot in the second energy level. There's a +7 nuclear charge attracting that, which is why if you were to bring an atom of fluorine close to an atom of sodium, it would be favorable for this electron to leave the sodium atom and go to the fluorine atom because there's a stronger pull. Also, this energy level is closer to the nucleus than this third energy level on sodium. So it's favorable energetically. It requires some energy to pull this electron away from the sodium, but energy is released when it gets added into the fluorine because that's a much more stable, lower energy state to be more strongly attracted to the nucleus of the fluorine atom. Now, fluorine, on the other hand, does not form an F with a -2 charge because in order to make the F -2 ion, it would need a third energy level because the second energy level is full. So if we put an electron out here in this hypothetical third energy level, the effective nuclear charge on this electron, we got 9 protons in the nucleus. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in between it and the nucleus. So this would be experiencing a -1 effective nuclear charge, and that's really no good. It would actually be repelled from the nucleus. So let's go back and just put this into just the original configurations. The thing to note, the electrons that are between the ones you're talking about and the nucleus are your shielding electrons. So for this electron in the third energy level, it is shielded by all of these electrons between it and the nucleus. Whereas the electrons in the second energy level are only shielded by the 1s electrons, and there's no shielding for those electrons. So I hope this helps make a little bit more sense of things. Keep in mind you can kind of get this from looking at the electron configurations as well, that the electrons in the first energy level provide shielding to the electrons in the second. The electrons in the first and the second shield the third energy level. So being able to figure out effective nuclear charge is going to play a key role. And then remembering, of course, Coulomb's law. Let's see, what am I doing here? The other thing to talk about with you, just to kind of show how this would work, is let's just take a look at one final example. We've got aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. So aluminum has 13 protons in the nucleus. Then you've got 2 electrons. Then we've got 8 electrons. I'm not a good artist. And then we've got 3 electrons. So in the innermost, we have a +13 effective nuclear charge for the first energy level. The second energy level is experiencing a +11, and the third energy level is experiencing a +3 effective nuclear charge. So these electrons are more tightly held than the electrons in, say, sodium atom, where they're only experiencing a +1 effective nuclear charge. But they're still out there. They can be fairly easily lost Aluminum does tend to lose all three of those electrons and form the aluminum with a +3 charge. But it never forms aluminum with a +4 charge because you've got this +11 effective nuclear charge going on for those core electrons. So, some key things to note as far as some terminology: these electrons in the third energy level are the valence electrons, and all the electrons that are closer to the nucleus are called core electrons. So, those are some key things to note. Um, Another thing to note is that effective nuclear charge is a periodic trend. All elements in the same group are going to have the same effective nuclear charge. So that's going to be something that you'll want to be aware of. For instance, if we go and look at this diagram right here, all the elements in group 1, their valence electrons are going to have a +1 effective nuclear charge, a +2 effective nuclear charge, a +3, +4, +5, +6, +7, and +8 effective nuclear charge on their valence electrons. The transition elements are kind of interesting that they all have a +2 effective nuclear charge because as you add a proton into the nucleus, you're also adding an electron, but you're not adding it in the case of, for instance, scandium, you're not adding it to the fourth energy level. You're adding it further into the nucleus into the third energy level. So you add a proton and you add a shielding electron. So they have the same effective nuclear charge on those valence electrons, which is why these elements in the transition metals tend to have fairly similar properties. And it gets even more similar with, say, the lanthanides or the actinides, where you're adding a proton and you're adding an electron 2 layers deeper into the nucleus. So, for for instance, with cerium, for instance, you're adding electrons now into the fourth energy level, while its valence electrons are on the sixth energy level. So, all of these elements have very similar properties and are quite difficult to separate from each other chemically. It can definitely be done, but it is a bit challenging. Hopefully, this helps give you a little bit better understanding. We're going to work with this even more tomorrow when we figure out how this applies to periodic trends that we actually observe.